My today's topic is to study the behavior of amplifier towards the signal with different component of frequencies. So this is the signal. Let it is made up of a multiple component of frequencies. Then the question arises, when the signal is amplified, then what happens to the gain? Is it constant for all the frequencies, or the gain becomes different for the different frequency components? Now, what is the requirement? The requirement to design an amplifier, to give uniform gain and phase delay over all the frequencies, that the good amplifier should amplify with equal gain to all the components and should give a phase delay the same for all the components. We know the audio amplifier, its frequency varies from 20 to 100 kilohertz. The video amplifier, the frequency goes up to 4.5 megahertz. Now our heading is the amplifier pass band. Good amplifier is one having the quality that is called fidelity of output. Fidelity of output mean that is output waveform should be identical to the input. And it will happen if the amplifier give a constant gain to all the components of the input signal. Practically, the signal which we deal are usually non-sinusoidal, and Fourier principle shows that such wave consists of a broad spectrum of harmonically related frequencies. To achieve the fidelity, all components of frequencies must be amplified, must be equally amplified in magnitude. What is an ideal amplifier? It is that which will have a constant gain, frequency response over all frequencies. But in real practice, it's never happened like this, as shown by the graphs. We define the two frequencies, F1 the lower frequency and F2 the upper frequency. There are three levels: low frequency, mid frequency, and the high frequency. Mid frequency is one where the gain of the amplifier remains constant. The lower frequency, the gain decreases. At the high frequency, gain of the amplifier again decreases. So we are going to define the two frequencies, F1 and F2. So here the gain remains constant, but at the lower side gain decreases, at the high side the gain decreases. Now here the gain falls to a specific value, and that is the frequency F1 and F2. And the between F2 and F1 is called the mid-frequency range. But what is F1? So let the constant gain as 1 unit, and F1 is defined as the gain. F1 defined as the gain where the gain falls to 1/√2 times the gain at the mid frequency. That is F1 and F2 defined as where the gain is 0.707 times the gain at the mid frequency level. So F1 and F2, where the gain has fallen to 0.707 times the gain which is at the mid-frequency level. We know the formula of the power equals to V0 square over R. Let it at the mid frequency, it is V0 square over R. But at F1 and F2, the output voltage falls to V naught over under root 2. So power becomes power P1 and P2 at frequency for F1 and F2 becomes V naught upon root 2 square upon R. That is V naught square upon 2 into R. That is 1 over 2 times the power which is at the mid-frequency level. So this is another definition of F1 and F2. So F1 and F2 are defined as the frequencies where the power becomes half of that power which is at the mid-frequency level. Now, what is the bandwidth? Bandwidth is defined as the frequency spectrum bounded by F1 and F2. That is delta F equals to F2 minus F1 in Hertz. So let me draw graphs. The frequencies, and they are more congested towards the right hand side because of the nonlinear scale. The width of the lines are not constant because the nonlinear scale of frequency. Along y-axis, that's A upon AM, left hand side low range, right hand side high range, and along y-axis the linear scale, but along x-axis the non-linear scale. So along low range F upon F1, high range F upon F2. For the low range frequency, relative frequency is taken. The frequency is varied with respect to F1. For high range, the frequency is varied with respect to F2. So the graph becomes like this. So we are interested here at F upon F1 is equals to 1 and F upon F2 equals to 1. That means the frequency F1 and F2. So at F1 and F2, the A upon AM is 0.707. The graph shows that if the frequency is less than F upon F1, the gain decreases. If frequency is higher, F upon F2, the gain again decreases. Now we plot a graph between relative phase delay versus F upon F1 and F upon F2. So here, relative phase continuously comes down and becomes 0 also, and then again down, negative. It varies from positive level to 0, 0 to then negative level. So this is relative phase delay. Now mid-frequency band is good where the gain and the phase delay both remains constant. And the symbols are AM and phi M. Now, circuit reactances are negligible within the mid-frequency range. Let there are two circuits, voltage source, series capacitor, and the resistor R. Current source, shunt capacitance with resistance R. Then if at the mid-frequency what happen? Series capacitor behaves as a closed circuit. Series capacitor behaves as a short circuit. There is no problem of the capacitance at the mid-frequency range. And shunt capacitor behaves as an open circuit. Again, there is no problem of the shunt capacitor for the mid-frequency level. So it acts as an open circuit. The shunt capacitor acts as an open circuit for the mid-frequencies. Now for higher frequency, what happens? Because omega is high, X is 1 over C omega. Omega is high, Xc decreases. So shunt capacitor cannot behave as an open circuit now. Here the shunt capacitance fall in reactance, and with the result it reduces the load impedance. It affects the load impedance because it is not behaving as an open circuit now. There is some value of the shunt capacitor at the high frequency. So with the result, it affects the output voltage. So it is creating the problem. Shunt capacitance creating the problem at the high frequency. So it is reducing the output voltage. Now the one question comes in mind of how the capacitance appears in the circuit. The shunt capacitance is due to the internal transistor circuitry. the higher frequencies. Shown in the graph. Due to the shunt capacitance, now we're coming the other side. Frequencies below the mid-frequency range, mean at the low frequencies. Now series capacitance at the mid-frequency it behaves as a short circuit, but it cannot behave short circuit at the low frequency, because when the omega is low, Xc becomes more and Xc increases at the low frequency. Now it cannot act as a short circuit as it was in case of the mid-frequency. So therefore there is always some voltage drop across the capacitor, with the result the output voltage, with the result the gain or the output voltage decreases with going towards the lower side of the frequencies. So series capacitance creates a problem at the low frequency region. Okay, thank you very much.